Well, hello everyone. Welcome to the Biotransport class at the University of Toledo. Today is Friday, March 27th, 2020, and we're continuing in Chapter 5 our discussion on mass transfer coefficients, looking at those special cases when we can get analytical solutions to the mass transfer coefficient and the Sherwood number correlation. So we'll continue that discussion. And also I just want to point out that next Friday, April 3rd, remember that's our second midterm exam. And I posted on the blog the way the exams will be handled now that we're online. So remember that I will post the midterm exam on the blog at 1 p.m. and I'll give you an additional half hour of time that you can work on the exam, plus I'll give you a half hour to convert your copy into a PDF file or some type of a file that you can email to me. So that means that I need to receive by email your copy of your exam by 3 p.m. So make sure that you allot the time between 1 and 3 p.m. next Friday, April 3rd for the exam. So that's all I have for now. Let's move on, and I'll talk about the material in the book then. Okay, what we want to do in today's lecture is dig a little deeper into the nature of the mass transfer coefficient and how we can describe both convection and diffusion using laminar boundary layer theory. And to introduce these ideas, we'll look at mass transfer and laminar boundary layer flow over a flat plate. And this will pick up on what we talked about back in Chapter 4 when we looked at just the boundary layer flow over a flat plate. We looked at the momentum transfer. And in this lecture, we'll look at both the momentum boundary layer and the concentration boundary layer, and you'll see how they mutually interact with each other. So figure 5.7 sets up the physical situation that we'll be talking about here. And let me zoom in just a little bit more here. So what we have then is we have a flat plate, and we have a fluid flowing over that plate. The fluid's approaching the plate with a free stream velocity of v, and as we know from Chapter 4, as that fluid interacts with the plate, the velocity of the fluid, because of the no-slip boundary condition at the plate, will go to 0, and momentum is then transferred from the region of high velocity, where it's lost due to frictional effects at the surface, and that sets up then a velocity gradient, and the relative change of that velocity turns into what we call the momentum boundary layer, which is shown by the dashed line right here. So the momentum boundary layer defines that region over which the velocity changes from 0 at the plate until we reach 99% of the free stream velocity, which is v. Now, for sake of argument, what we'll say is that on the surface of the plate we have a solute that has a surface concentration, CAS, everywhere the same on the plate. That would be the equilibrium solubility of the solute, for example. And we'll treat the concentration of the solute out here in the bulk solution as 0. And what will happen is because of the interaction between the momentum processes and the mass transfer processes, we'll actually develop a concentration profile and a concentration boundary layer, which we call delta sub C. So the boundary layer for concentration is defined as that region over which the solute concentration changes from the CAS value at the surface to 0 right here, where it meets up with the bulk of the fluid out here, which is at a 0 concentration. Now what we'll do is we'll focus on a shell volume here of length extending from x to x plus delta x. We'll look at it within the concentration boundary layer, so its height is delta c of x, and the whole thing is going into the paper with W. So W would be normal to the paper. And what this means then is this really sets up a two-dimensional problem where the coordinate system is just x and y, as I have drawn there. So now what we'll do is we'll first do we'll first perform a steady state solute balance on this shell volume, which is then given by equation 5(120). And what we're looking at then is the rate at which mass enters that control volume, which is given by this term right here, minus the rate at which it flows out of that control volume due to convection in the x direction. So that's what the Vx would be. And if you think of this as a little thickness, a slice of thickness dy, then dy times w, that's the surface area normal to that Vx velocity at some position y, so that would give us a volumetric flow rate times the concentration, gives us the mass rate terms that I was talking about. So remember, these equations have to talk to you. You have to look at each term and you have to reconcile what those terms mean in terms of the physics of the problem. Also, we know we have a velocity up here at the top of the box, and that velocity is going to be carrying solute with it, and the area that's normal to the top of the box up there is W delta x. So this would represent the amount of solute that leaves our control volume due to convective flow in the y direction. And then down here at the surface of the plate, we would have the solute flux, which would be NaY, so that would be the y component of the solute flux vector evaluated at y equal to 0, and the area normal to that NaY would be W times delta x. Now at steady state, all of this has to equal 0. So what we can do is we can rearrange this equation, and we can solve for the flux at the surface of the plate, and that's given by equation 5(121). So we end up with this equation, and then what we do is we use Fick's first law to write the flux of the solute in terms of the concentration gradient and the diffusivity. So that's how we get to equation 5(122). Now, in order to solve that particular equation, we need to know how Vx and the solute concentration depend on both x and y in their respective boundary layers. Now remember, back in chapter 4 we developed equation 470 using a similar boundary layer approach for the momentum processes that are occurring in this flow, and that's given by equation 470. So this is the velocity profile in the boundary layer, and then what we can do is we can do a similar thing and write that the solute concentration profile in its boundary layer is also given by a cubic equation. Now remember, we're basically solving these differential equations in an approximate manner, but as we showed in chapter 4, these solutions are very accurate, certainly accurate enough for our engineering calculations. So in order to use equation 5(123), we got to find the four constants A of C, B of C, C of C, and D of C, and that's where we introduce these boundary conditions. So these are the boundary conditions for the solute at y equal to 0 when you're at the surface. The concentration we know is CAS. When we get to the edge of the boundary layer, the concentration of the solute goes to 0. and also at y equal to at y equal to the when you're at the edge of that boundary layer, the first derivative of the concentration profile would also be 0. So it's reaching it, and the condition on that profile would be that its slope is equal to 0. And then at y equal to 0, basically we're saying that from Fick's first law that the flux at the surface only depends on x. It doesn't depend on y, and that gives you the condition that the second derivative of the concentration would be equal to 0. Now, when we introduce these boundary conditions, especially boundary condition 2, we lose that convective term out the top of the box, and we just end up with this differential equation right here that would need to be solved. Now, if you take equation 5.123, which we had up here, right there, and if you use these boundary conditions to find the four constants a through d, you end up then with equation 5.126, which is the concentration profile of the solute within its boundary layer, delta C. Now, the thing we don't know in equation 5.126 is we still don't have an equation for how the concentration boundary layer changes with x. But that's where we will introduce equation 5.126 as well as equation 470 in here in this integral term, and if we crank that all out, we can then end up with a way to determine what the value of the concentration boundary layer thickness is as a function of x. So that's what I'm talking about up here at the top of the next page, and we'll also assume that the ratio of the boundary layer thicknesses, and we'll call that delta, capital delta, is equal to the ratio of the concentration boundary layer thickness and the momentum boundary layer thickness at any value of x. And it actually turns out that for the geometry of a flat plate, that delta is in fact a constant. So the variations of these two boundary layer thickness in terms of their x dependence cancels out. And this has been shown to be true by more advanced solution techniques. But here, when we're getting an approximate solution, we'll make use of that and assume that that capital delta is in fact 0. Now, when you plug everything back in, as I was talking about earlier, you put the velocity profile, the concentration profile in there, and you crank it all out. The algebra is a bit overwhelming, but what you can end up with is you can show that the differential equation for the concentration boundary layer equation is given by equation 5.127. And the boundary condition on this guy would be that at x equal to 0, the concentration boundary layer is equal to 0. Now, this differential equation is easy to integrate. Just separate the variables, bring the delta C over here with the d delta C, and bring everybody else to the right hand side. And when you do that, you can easily integrate this equation, and you end up with equation 5.128, which tells you how the concentration boundary layer depends on x. And also buried in there, we still have that delta term in there, and we have to figure out what the delta term is. How do we know what the delta term is? Well, that's the next thing we want to take a look at, is what is the ratio of the boundary layer thicknesses. Well, if we go back to chapter 4, equation 472, we previously showed that the momentum boundary layer thickness is given by this particular equation here, which we call back then equation 472. So if we divide equation 5128 by equation 472, that's our definition of delta. So we can take the ratio of these two equations and we end up with equation 5129. Now this equation is really interesting because, you know, we've been talking about the Schmidt number as another dimensionless number, and that shows up in mass transfer, and now we see through this boundary layer analysis the natural showing up of the Schmidt number. The Schmidt number is defined as mu divided by rho dAB, or nu divided by dAB. So what we're seeing now in equation 5129 is that this ratio of the concentration boundary layer thickness to the momentum boundary layer thickness is connected to the value of the Schmidt number. And the Schmidt number only depends on the properties of the solute and the properties of the fluid in which that solute is diffusing. So this is a very interesting result then that comes from boundary layer theory. Now there's a couple situations that will drive the magnitude of the Schmidt number, and we can get an idea from that then of whether the concentration boundary layer lies within the momentum boundary layer or if the momentum boundary layer lies within the concentration boundary layer. And I talk about this in the next paragraph right here. So for solutes diffusing through liquids, which is pretty much the situation that bioengineers would be interested in, the Schmidt number is generally much larger than unity. If you've been following some of the examples, the Schmidt number for a solute in water can be on the order of 1,000 or more. So from equation 529, we would then have, if the Schmidt number, say, is on the order of 1,000, that makes this number right here very small. It'd be like 0.001. And the only way that we could end up with a very small number over here, like 0.001, is if the delta term itself is very small. Okay, because you'd have to have a very small number over here to get a very small number right there. So what that means then is that delta has to be less than 1 for a solute diffusing in a liquid, and if delta is less than 1, then that means from this definition of delta that we see then that the momentum boundary layer thickness will be greater than the concentration boundary layer thickness. So for a solute in liquids, we can always say that the concentration boundary layer lies well within the momentum boundary layer. And that's what I say right there. Now for solutes diffusing through gases, it turns out that the Schmidt number is on the order of unity. I think for diffusion of oxygen in air, the Schmidt number is like on the order of 0.7 or something like that. So if you have diffusion in gases and the Schmidt number is on the order of 1, then that means this term right here is on the order of 1. And if we look at this expression right here, the only way we could get 1 over here is if delta itself is on the order of 1. And if delta itself is on the order of 1, that means that the concentration boundary layer and the momentum boundary layer actually have pretty much the same thickness. And that's what I'm saying right here, that for gases, the momentum boundary layer and the concentration boundary layer are pretty much the same. The other condition would be for solutes diffusing through materials like liquid metals. Liquid metals have the property then that the Schmidt number is much less than unity. They have very low viscosity, and in that particular case, that's going to make the delta way bigger than 1, and the concentration boundary layer then will be lying outside of the momentum boundary layer. For us as bioengineers, we don't deal much with liquid metals, but it's just an interesting thing to point out. So in general, if one knows the value of the Schmidt number, the mass transfer problem being considered, then equation 5(129), let's see, can be solved for the value of delta. Okay, and then knowing the value of delta, the velocity boundary layer thickness is then given by equation 472, and you can get the concentration boundary layer thickness by multiplying that value by your particular delta. Now, for many mass transfer problems that we'll be interested in, the solute is diffusing within a liquid, so we know that the Schmidt number is much larger than unity. This makes the right-hand side of equation 5(129) much smaller than unity, and the only way that can happen is if delta is also much smaller than unity, as we discussed earlier. So this gives us the interesting result that the concentration boundary layer lies well within the boundary layer for the velocity, and we can show from equation 529 then that for delta being much smaller than 1, equation 5(129) simplifies to the following result that tells us that delta is proportional to the Schmidt number to the minus 1/3. Now remember that when we started talking about mass transfer coefficients and Sherwood number correlations, I was telling you how the Schmidt number always seems, and 99% of the time, that the Schmidt number shows up in these correlations as being to the 1/3 power. And that 1/3 power is coming about through this boundary layer analysis that we're talking about for liquids. Now on the next page, what we want to do, we don't want to lose sight of the fact that what we're after is trying to figure out what the mass transfer coefficient is for laminar boundary layer flow over a flat plate. And laminar boundary layer flow over a flat plate is very similar to the types of flow situations that we have in all kinds of biomedical devices. So if we take the last results that we've developed, we can develop the relationship between the thickness of the concentration boundary layer and the position downstream along the plate. So when you work out the algebra of all of that, you can see that the boundary layer thickness for concentration is given by 4.64 times 1 over the Reynolds number to the 1/2, 1 over the Schmidt number to the 1/3. Remember, it's the concentration boundary layer thickness that is providing the resistance to the mass transfer. So the thicker the boundary layer, the less mass transfer you're going to have. So to get the mass transfer coefficient, what we do here is recall that the mass transfer coefficient is proportional to the solute diffusivity and inversely proportional to the concentration boundary layer thickness. So this means that since delta C depends on x, the mass transfer coefficient will also depend on the location along the surface of the flat plate. And we see that if you go back and you look at equation 5(131), you see that the boundary layer, concentration boundary layer thickness depends on x. So we can calculate the local value of the mass transfer coefficient using equation 574, which says then that the local mass transfer coefficient is given by this equation. So this part right here just comes from our definition of the mass transfer coefficient in terms of Fick's first law. Notice that we evaluate the gradient here at the surface. Now, as part of our boundary layer analysis, we already developed an equation for the concentration profile, and we can substitute that in for this derivative and evaluate it at y equal to 0. So when you do all of that, crank through the algebra for that, we develop then the Sherwood number, or the mass transfer coefficient, for laminar boundary layer flow over a flat plate as given by equation 5(133). So this is our local mass transfer coefficient equation that describes this situation. Here's the Sherwood number. You can see the local value is proportional to the Reynolds number to the 1/2 power, and we see the Schmidt number in there to the 1/3 power, and if you just write it in terms of the Reynolds and the Schmidt number, it looks like this. And the little x on the Reynolds number is just to remind you that the characteristic dimension in the Reynolds number is the local position x. Now if we want to get the average mass transfer coefficient, the average mass transfer coefficient would be over the entire area of the plate, which would be L times W. So for a plate of length L, the average mass transfer coefficient by definition would be given by this equation. So it's just really taking the mean value of the local mass transfer coefficient. So if we take equation 5,133 and we put that in the 5,134, crank out the integration, we obtain the equation 5,135 for the length average mass transfer coefficient, which is then given by this equation. You can see that the length average mass transfer coefficient based on the length L, when x is equal to L, is just twice the local value. But you can see the same dependence on the Reynolds number to the 1/2, Schmidt number to the 1/3. And this equation works for laminar boundary layer flow over a flat plate up to a Reynolds number of 300,000. Above 300,000 we transition into turbulent flow. Now how you use the average mass transfer coefficient, we talk about that up here at the top of the next page. So for flow over one side of a flat plate of length L and W, the solute transport rate can then be obtained as follows. Okay, we recall that the surface concentration is CAS, and we'll let CA bulk be the bulk concentration. Now it turns out, I'm not going to get into the math of all of this, that even though we derive the mass transfer coefficient assuming that the concentration in the bulk solution was 0, the result that we actually get mathematically for that mass transfer coefficient turns out to be independent of what the concentration in the bulk solution is. It comes about because the describing differential equations are homogeneous, and if we have a non-homogeneous boundary condition like a CA bulk, we can remove that very easily, and when you solve the equations you end up with the same result. So bottom line then, if you have a plate, one-sided is coated, and the total surface area is L times W, then we just use this equation that we talked about earlier, which is our defining mass transfer rate relationship, and the Km that you use in this equation is the length averaged mass transfer coefficient that we just derived. So let's see how we put numbers into all of this. And that's what's shown in example 515. Just gives us a chance to crank through some numbers. But imagine you got blood flowing across a flat surface of a polymeric material coated with an anticoagulant drug. Equilibrium studies of the drug coated on the polymer show that the drug has a solubility of 100 milligrams per liter of blood. The fluid adjacent to the plate equilibrates quickly, hence the concentration of the drug at the surface of the plate is CAS. And what we want to find then is the distance at which the laminar boundary layer flow over the surface of the plate ends. Where does it end? When do you transition to turbulent flow? We want to know the thickness of the velocity and concentration boundary layers at the end of the polymeric material, where that transition happens. We want to calculate the local mass transfer coefficient, and we want to calculate the average mass transfer coefficient, and we'll assume that the concentration of the solute in the bulk is equal to 0. We assume that the blood traveling across the polymeric material has a free stream velocity of 40 centimeters per second. The polymeric material has a length in the direction of flow of 30 centimeters, and the diffusivity of the drug in blood is given as 4.3 times 10 to the minus 6. So those are all listed right there. I didn't scroll down, but you can read those now for yourself. So let's talk about the solution then. We just jump in and start calculating things. For part A, we use the fact that the transition to turbulence begins when the Reynolds number hits 300,000. So we can use this equation to determine the distance downstream when that happens. And when you do the calculation, put the numbers in, you get an X of 213 centimeters. And the actual plate's only 30 centimeters in length. So we know then over the 30 centimeters that we're interested in, we can apply the laminar boundary layer flow results. For part B, we use equation 472 and 5130. We can calculate the boundary layer thicknesses at the end of the polymeric material. That's where L is equal to 30 centimeters. We calculate the thickness of the momentum boundary layer, comes out to be 0.68 centimeters. At the top of the next page, we calculate the Schmidt number for this problem. So here's the Schmidt number calculation. We need the Schmidt number in order to calculate the concentration boundary layer thickness. Put in all the numbers, we get a Schmidt number of 6607, which is typical of the Schmidt number for a large solute diffusing in a viscous material. So the Schmidt number is greater than 1, and the concentration boundary layer therefore will lie within the velocity boundary layer, and we can calculate that thickness in terms of the Schmidt number and the momentum boundary layer thickness as I show here, and that comes out to be 0.036 centimeters. And we find then that the concentration boundary layer is considerably thinner than that of the momentum boundary layer. For part C, we calculate the local and average mass transfer coefficients at the end of the plate. The Reynolds number at the end of the polymeric surface is given by this right here. So we see we got a Reynolds number of 42,240. We're well below the 300,000 limit there. So we're okay in terms of still being in laminar flow. And from equation 5133, we calculate the local mass transfer coefficient. We get that number. And then the average mass transfer coefficient is just going to be 2 times that value. So we get 3.56 times 10 to the minus 4th centimeters per second. The average mass transfer flux of the drug from the polymeric surface is found from equation 5136. Remember, the solute flux at the surface would be given by the m dot A divided by the surface area. So that would just mean that the average solute flux would be Km times CAS. And when you crank that out, this would be your average flux from the entire surface. So that's laminar boundary layer theory as applied to diffusion from a flat plate. And we got some interesting results from that. We see naturally where the Schmidt number comes about and how we interpret the Schmidt number in terms of the thicknesses of the momentum and concentration boundary layers. What we want to do now is start thinking about, well, what happens inside of a tube? If I have fluid flowing in a tube, and suppose I have a solute coated on the surface of that tube that's diffusing into the fluid flowing through the tube, what happens in that situation? And that's the next problem that we'll look at. And the first way to look at this problem is through what we call the short contact time solution. So what we're going to do, and it's called mass transfer between the wall of a cylindrical tube and a fluid in laminar flow. And the mathematics are very interesting. I'm going to skip through and just point out the key results, and I'll explain the physical situation and what some of the assumptions are that we're making. You know, I'd encourage you to look through the math and also On the blog in that section, Chapter 5 stuff, there's a couple additional information sheets that talk about the derivations of some of the equations that are in this particular section. But what we really want to get to is we want to get to a correlation for the Sherwood number that would allow us to calculate the mass transfer coefficient for laminar flow in a cylindrical tube. And in this case here, in order to get an analytical solution, we have to make an important assumption, and that's going to be the short contact time solution. So the physical situation that we're talking about is shown here at the top of the next page. So what we have is we have a cylindrical tube. That's what the solid lines represent. And then at some distance downstream, we have a region of constant wall concentration, CAS. The fluid flowing through this tube enters back over here, and by the time we get to the region where we have solute on the surface of the tube, we have a fully developed laminar velocity profile. So what that means is that the mass transfer only starts to happen once the fully developed laminar velocity profile makes contact with that region that contains the solute. In this previous region over here, remember the fluid comes in and the velocity profile is going to be flat as it makes contact with the tubes, and then as it starts to flow, the velocity profile develops. So it takes a certain distance before we get this fully developed velocity profile. Now, in order to account for mass transfer when you have a developing velocity profile, and also that means developing concentration profiles as well, there's really no good analytical way to solve that problem, and what people do is they've done experiments then for those situations and have developed Sherwood number correlations that handle the situation when you can't invoke what we're going to be talking about as the short contact time solution. So what we'll do first is look at the short contact time solution, and then we'll look at the more generalized correlations that have been developed from experiments. So basically, if you read through this page here, you can study the math on your own, and like I said, the math is pretty interesting, and what's happening here is what's happening here is that with the short contact time solution, we're basically saying that the solute diffusing from the surface of the tube does not penetrate very far into the tube. So one way to look at that would be that the residence time of the fluid in the tube, would be the length of the tube divided by its velocity. That would tell you how many seconds, for instance, the fluid spends inside the tube. And if that number is small relative to the time it takes to diffuse from the surface, say, to get to the center, which is going to be, that diffusion time is going to be proportional to the radius of the tube squared divided by the solute diffusivity. If that diffusion time is way bigger than the residence time of the fluid, then we wouldn't expect the solute to diffuse very far into the fluid. Now, when you go through all the math, you can come up with equation 5148, which tells you what the concentration boundary layer thickness is. This would be the distance to which the solute has diffused into the fluid at any particular value of Z. So this delta C would be from the surface of the tube into the fluid. Now, you as the engineer, you would know the average velocity of your fluid, you'd know the diffusivity, you'd know the radius of the tube, and one particular location of interest would be when Z is equal to L, because that would give you the maximum thickness of the solute boundary layer. So you would be able to calculate what that value of delta C is, say at Z equal to L. And if delta C comes out to be much, much smaller than the radius of the tube, then you would know that your short contact time solution is a valid solution. If it's not, then if delta C is, say, on the order of R, then that's telling you that the short contact time solution is not a valid approach, and you'd have to use one of those more general correlations that are obtained experimentally. Also, what we can do is we can get a mass transfer coefficient for this situation of the short contact time, and we start with the flux term right here. The flux in the R direction at the surface of the tube, R equal to capital R by Fick's first law, is given by this expression. And in the previous math that was developed, we were able to calculate what the concentration gradient is. So when you crank that all out, you end up with equation 149, which tells you what the flux is. And then from our definition of the flux and the mass transfer coefficient, as shown in the next equation, we can get the local mass transfer coefficient. So here's your local mass transfer coefficient. Notice that the local mass transfer coefficient is inversely proportional to the downstream distance Z to the 1/3 power. So as you move down the tube, that is telling you that the boundary layer adjacent to the tube wall is getting thicker and thicker, and that reduces the mass transfer coefficient. If you play around with this equation, you can get it in the form of a Sherwood number, and this would then be the local Sherwood number. And you can see that the local Sherwood number is a constant times the Reynolds number. This term right there is the Reynolds number. Note that the power in this case is to the 1/3 power. The Schmidt number once again naturally pops up, and it's to the 1/3 power. And then we have a term here also to the 1/3 power, which is the ratio of the diameter of the tube to your downstream position Z. So that's the position dependence, and that's what makes the Sherwood number local. If we take the local mass transfer coefficient and we average it along the length of the tube, as shown here, crank out the math, we end up with the star equation down here, which is the Sherwood number for laminar flow in a cylindrical tube for the short contact time solution. We have a constant 1.615 times the Reynolds number to the 1/3 times the Schmidt number to the 1/3 times the diameter of the tube divided by the length to the 1/3 power. So how we use these equations for design calculations, first, if you're looking at mass transfer within a tube, you'd have to ask yourself, am I going to assume that I can use the short contact time solution? So that's the first decision you would have to make. And then if you say, okay, I'm going to give it a go, or I know that my delta C at Z equal to L is less than my radius of the tube, so I know it would be a decent assumption. Then, in order to calculate the mass transfer rate of the solute from the surface of the tube, then we would invoke this equation that we've been using to describe the mass transfer rate. So that would just be our average mass transfer coefficient Km. Our surface area for a tube would be 2 pi r times L. And the driving force in this particular case, the way the equations get set up, because the bulk concentration, since the solute only penetrates a very short distance into the fluid, the actual bulk concentration is still whatever it was coming into the tube. So that's why the driving force is based on the entering solute concentration, and the driving force is then the surface concentration minus that entering concentration. Now the overall solute mass balance, usually in these kinds of problems, what you're interested in finding is what's the concentration of my solute exiting the tube. So in other words, maybe I've got plasma entering a hollow fiber unit, it's got 10,000 tubes. I want to know what my solute concentration is going to be as the fluid leaves this hollow fiber unit based on diffusing solute from the surface of the fibers. So to find that exiting concentration, then we have to do an overall solute mass balance. In this case, it's applied to the situation of the short contact time. So if the fluid exiting the cylindrical tube is completely mixed, in other words, as that tube comes out and enters a storage vessel or some other process, everybody gets mixed together. So the bulk fluid gets mixed together with the fluid within the concentration boundary layers. Those concentrations all mix together. And what we have coming out then is just a bulk concentration of the solute, and we assume that that solution is well mixed. So a simple mass balance at steady state then would say that the total amount of solute leaving the device, as given by this equation here, has to equal the total amount of solute that's coming into the device plus the total amount of mass transfer. So this is where we see our mass transfer rate equation coming in to our overall mass balance on a device that we're investigating. So that's going to be your Km times your surface area times your driving force. So we can take this equation and we can solve then for the exiting concentration, and we get equation 5156. So you as the engineer, you would know everything on the right hand side for your particular design situation, and you could calculate what the exiting concentration would be. And this is illustrated in the next example, 516. Example 516 says plasma is flowing at an average velocity of 15 centimeters per second through a tube that is 1 centimeter in diameter. The walls of the tube are coated over a length of 10 centimeters with a drug that diffuses from the surface of the tube into the flowing fluid. The equilibrium concentration of the drug in the plasma is given as that. Find the average mass transfer coefficient over the 10 centimeter length that's coated with the drug. Also find the total transport rate of the solute and the mixed concentration of the drug in the plasma after the coated section of the tube. Show that the short contact time solution is a valid approach for solving this problem, and then we're given the diffusivity of the drug in the plasma. So the first thing we want to do is calculate the Reynolds number, which I show down here. So you take all the properties, put them into the Reynolds number. We get 1,280, which tells us that we have laminar flow, which is good. So knowing that we have laminar flow, we can apply the short contact time solution for laminar flow mass transfer in a cylindrical tube. So we calculate the Schmidt number, as I show right here. You can see it's almost 3,000. And then using equation 5153, we calculate the average Sherwood number. So we pop in those Reynolds and Schmidt numbers, crank it all out. We get a Sherwood number of 116. And then from the Sherwood number and its definition, we can calculate the average mass transfer coefficient, as shown right there. So we have our average mass transfer coefficient. Now we can go to equation 5154. We can calculate the mass transfer rate of the solute from the surface of the tube. So we plug in the numbers. That tells us that over the entire length of the tube, we're transporting 0.0015 milligrams per second of the substance that's on the surface of the tube. And then from equation 5156, we can calculate the concentration of the material, of the solute, as it leaves the tube. So we just take 5156, we don't have anything coming in the feed plasma, so that equation simplifies a little bit. We pop in the numbers and we get 0.124 milligrams per liter. Now we want to check to make sure that the short contact time solution is valid, so we can calculate the thickness of the concentration boundary layer at the end of the coated section of the tube from equation 5.148. So this is where we check our delta C, and you can see we end up with a boundary layer thickness for the solute of about 0.02 centimeters. This value of that boundary layer thickness is quite a bit less than the tube radius of 0.5 centimeters. Hence, we'd feel good about using the short contact time solution for this mass transfer process that we're studying. Another way to look at this is whether the short contact time solution is valid is to compare the characteristic time for solute convection and the time for radial diffusion within the tube. I talked about that a little bit ago, but now we can apply that idea right here, and that's talked about here at the top of the next page. And the characteristic resonance time of the fluid flowing through the tube would be the length of the tube divided by the average velocity, which comes out to be 0.67 seconds. The radial diffusion time for the solute is on the order of r squared divided by the diffusivity. So if you calculate the diffusion time, it's like 62,000 seconds. That would be the length of time, an order of magnitude estimate of the length of the time for the solute to reach the center line of the tube. And when you compare that to the time that the fluid is in the tube, there's just no way that the solute's going to make it to the center of the tube, and we would make, from that we could make the conclusion that a short contact time would be valid. Okay, so that really wraps up the cases I wanted to show you where we could analytically derive expressions for the mass transfer coefficient in laminar flow. So we looked at several special cases of that, and from those solutions we also got analytical correlations for the Sherwood number. What we'll do next time is we'll just talk about the general case of mass transfer between the wall of a cylindrical tube and a flowing fluid, and this is where we'll start to introduce these generalized mass transfer correlations for the Sherwood number that come from experiments. So see you back here on Monday.